to have with us today Alesandra Bianchi from the University of Padova. She will be speaking, as you can see, on random walks on the Lévy-type random media. And I just remember you that if you wish to ask questions, so please use the chat, and then I will transmit the question to Alesandra. So Alesandra, it's a great pleasure to have you. And well, we're looking forward to your.
Thanks a lot, Claudio, for the invitation. It's a great pleasure for me to have the opportunity to speak to this Brazilian audience, and I'm still hoping to go back in Rio de Janeiro at TIMPA soon when it will be possible. So the work I'm going to present, let me say that is a collection of results that has been published collected in 3 papers. 2 have been published, and the 3rd one is on the archive. Anyway, all the 3 are on the archive, and they are how to say, the product of a collaboration with many other people I will mention along the talk, in particular Marco Lenci from the University of Bologna and Giampaolo Cristodoro from the University of Milano Bicocca, who are the ones with whom I start this project. And then on the French side, we have Françoise Pen, the University of Pest, and in between the youngest one, there is Elena Magnanini, which is here in Padova, Samuele Stivanello also here in Padova, and Gianmarco Beck from the University of Florence. Anyway, to gentle start with the seminar. So this is the outline. So I will base in the first part, I will present the model that can be looked at as a random walk on a point process. In fact, before introducing the model, I will start with the very classical results of random walk. Forgive me for that, but this will give me the opportunity to fix the notation and give an idea of the kind of result we are looking for. And the second part, I will present the results, some idea of the proof. And in the third part, I will go to the generalized model. The model that we study is a one-dimensional model. So in between the generalization, there are the two-dimensional model, but also other connected model. So as I said, I'm starting with something that is really classical. It is a random walk on RD. Ci are then a sequence of i.i.d. Random variable that we can assume that are centered, otherwise we can center them, taking value on RD and with covariant matrix sigma. If you want, you can think just to the one-dimensional case, as essentially I will state on that dimension. And then the random walk, of course, is as a trajectory defined through this random variable Sn that represent the partial sum of the from 0 to n of the variable ck. And of course, by definition, is also a center random variable, and with covariant matrix that in fact increase with n linearly with n. In fact, is under this hypothesis just n sigma. In particular, this immediately identify that the scaling limit for the CLT, in the sense that if we look at the mean square distance of the motion from the origin, we see that E increase with n, sigma square is a constant related to the covariance matrix. And then we call this diffusing scaling because if we divide the random variable Sn by square root of n, indeed we have our convergence in distribution to a Gaussian normal law which is centered with the covariance matrix sigma. This is very standard. In fact, another quite basic fact is that these results can be straighten by considering to get a functional limit theorem by considering the sequence of processes S and T. These are processes on defined on R plus positive time that are obtained by looking at the position of the random walk S at time nt divided by square root of n. So in this setting, we have the following Nonscaling variance principle that states the convergence in distribution of the process, or weakly convergence. Here we'll use we'll refer to weakly convergence to differentiate it from the convergence of the random variable at fixed time. Weakly convergence to the Brownian motion. This is a Brownian motion that so that at time t, bt is a Gaussian variable with the covariance t times sigma. This convergence holds, this is the notation I use in this, I don't know if you see the pointer here, maybe not. It works. Holds in this space, that is the set of Cadillac function D defined on, actually this is R plus, and with the spherical topology J1. If you want to, feel free to ask me about that. Otherwise, I go on and maybe we can go back later to this better definition. Of course, in this case, the Brownian motion has almost surely continuous trajectory, so the result can be even bring to the space of continuous function with respect to the uniform norm. But this is the context that I will need in the sepal. And now again, let me remark that again, this asymptotic process has a diffusive scaling in the sense that is the mean square distance from the origin increase in time with linearly in t. So globally, if we look at the trajectory of this process, either the random walk, either the asymptotic process, we have a kind of diffusive trajectory as the one that you see. Of course, in the discrete time setting, you have to make an interpolation of time to get a continuous object. However, you have, if you look at it from very far, you have more or less the same object. This is a diffusive trajectory that generally is characterized by this short disorder motion that makes the mean square displacement of the process increase in time, linearly in time. This behavior characterizes a very huge number of natural systems. Just to give an idea, it may be used to describe the motion of the dust particle within smaller molecules of gas, but also the motion of a star within galaxy, and going out from a physical system, for example, can be used to describe the fluctuation in the stock market. However, this behavior is universal in the sense that appear in many different contexts, but of course there might happen different behavior, and in particular I want to focus on this, let me call it a super-diffusive behavior. The picture shows a kind of super-diffusive trajectory that is now characterized again by the presence of this area of short disorder motion, but they are alternated with this long ballistic flight. Okay, so straight path, very long straight path. The presence of this one in particular yields a super-diffusive behavior in the sense that if you look at the mean square distance from the origin of the process, it increases more than linearly. In particular, it increases as t to the delta, while delta is bigger than 1. And this behavior also characterizes many natural systems, in particular in connection with the motion in disorder medial. For example, the motion of a light particle in an optical lattice, the tracer in a turbulent flow, or the molecular diffusion in porous media. So the model that we want to describe, we are going to describe, want to modelize this kind of behavior. Of course, the simple things that one can think about is to consider a stable random variable. So assume, for example, to take again a sequence of ideal real random variables vita k that are in the domain of attraction of alpha stable random variable. This means that essentially the tail has this power law, so decays with a power minus alpha. And when alpha is in between 0, 1, this means that this random variable do not have infinite variance or even infinite mean. In particular, they do not satisfy the hypothesis of the CLT or even of the low large number. Okay. However, thanks to the alpha stability, to the convergence to this alpha stable random variable, if we denote by Sn the random walk, so obtain as by taking the partial sum of this random variable, this is a random walk on R in one dimension. We can still derive a limit theorem that is a non-standard CLT. Where what happens is that if alpha is in between 0 and 1, then if we divide Sn by, we have to divide Sn by n to the 1 over alpha to get a convergence in distribution. Notice that if alpha is in between 0 and 1, 1 over alpha is bigger than 1. So we don't even have a low large number in that situation. If alpha is in between 0 and 2, this means that the process in principle is finite mean. Then, if we center the process with by subtracting mu n and again divided by n to the 1 over alpha, again we have the convergence in distribution. The two, I mean, we can easily memorize the two, but by assuming that mu is equal to 0, so centering, when possible, centering the random variable zeta k. And this represents a non-standard CLT because, first of all, the scaling is not diffusive. We are not divided by square root of n, and the limit in the distribution is not a Gaussian. And of course, as for the classical random walk, we can try to straighten this result to a functional limit theorem that see that the CLT has a particular case when taking t equal to 1. So just to easy the notation, let's consider just the case in which mu is equal to 0. So center a random variable. Again, we define this process, this sequence of process and SNT by taking the random walk at time, the integral part of nt divided by n to the 1 over alpha. And then in a similar way, we get the weakly convergence of the process to a Levy process that is alpha stable. An alpha process Z. These in the space of Cadillac function, the alpha process in principle are almost surely right continuous functions, so they may display jump, indeed. And in fact, by the alpha stability, it turns out that Zt indeed the scale is equal to the distribution to t to the 1 over alpha zeta 1. So this means that in particular its second moment it's increase like t to the 2 over alpha. So is bigger than linear. Okay. Very well. Of course, this is a process in R, but in fact, a similar construction can be generalized to RD by considering the Lévy flies. The Lévy flies are very used in physical, very mentioned in physical study, in particular in the physical literature, and are random walk on RD with i.i.d. jumps that are taken with a uniform direction and independent length with alpha stable distribution, again with alpha between 0 and 2. Now, okay, if we go back for one moment to the physical system, so to the modalization that we have in mind, on one end, we have that this process have infinite variance at each finite time, this by definition. And this is not really a physical property. If you want, I can go back, but maybe it's not necessary to the previous slide to realize that. Okay, anyway, so at each finite time, they have an infinite variance. This is not a physical property. However, we can solve, at least this problem is usually solved in a simple way by considering the Levy walks. Levy walks are, maybe the word is a bit misleading, because Levy walks are continuous time Markov process on RD that are just obtained by linear interpolation of the Levy flight, which means that the trajectory of the process X follows the process Y, but the jumps are now covered at a finite, say, one velocity. So we don't have a sudden jump, but a straight line, how to say. And in fact, this give rise to a super-diffusive motion and provide this, for example, in one dimension, this Levy skin, where we have finite second mode that decrease in time more than linearly. So good. This is the super-diffusive behavior that we want to get, the kind of super-diffusive behavior that we want to get. But again, coming back to the physical system, what is a bit unsatisfactory is that the super-diffusive behavior is intrinsic to the Walker motion and independent of the media. So it's the Walker that decide to move with this very long jump. So in a sense, this is a good behavior, but the model are naive, useful, very much studied, but in a sense naive. So we want to go further than this, and so finally, let me define the random walk and random media that on which we will focus on. This was introduced by Barkay, Florev, and Klafter in 2000 with the name of Levy-Lorentz gas, or at least essentially related to this. To define the model, I need two objects. First, a media or environment, omega, that will be choose to be a renewal point process on R, so that the interdistances between the point are these random alpha-stable random variable zeta k. Okay, so we place a first point on the variable in 0, and then all the others at independent distance zeta k. This will be the random environment of a Lévy-type, or random median on Lévy-type, that the construction is as you see in this picture. Okay, the red circle are the point of the environment, and then the distance in between them are these blue segments. And then the second ingredient is what we will call the underlying random walk. That is a classical random walk on Z, centered and with finite variance. At least at this moment, we consider this hypothesis. And now we are interested essentially in two processes. First one is a discrete time processes, Y. That is the random walk on the point process omega. And this is the random walk. This is obtained coupling with a coupling with to S, to the underlying random walk S, which means that the process Y at time n is exactly given by the position of the point of the process with label Sn. So it's given essentially by the composition of omega with S in n. So essentially, this is a simple representation. In green, we have our underlying random walk on Z. And then below, we have our process Y that move on the point of omega, which is a subset of R, following essentially the underlying random walk S. Is it clear up to now?
Very clear.
Even too much. And then it would be all very clear. And then the second process we are interested in here is this continuous time process X that is constructing, how to say, with the same philosophy that Levy walks are obtained from Lévy-flight. That is just interpolating the jumps of Y at constant 1 velocity. I will draw a picture. Let me just say that to formalize and actually to introduce a notation that I need in the sequel, let Tn denote the length of the walk up to the n jump. So Tn is this length, is given by this summation, and it is called collision time. Okay, now, okay, it's a length, but it's a time. So what happened? The point is that, as I said, if x move at constant 1 velocity, the length of its path will correspond so essentially to the time it will take to cover the path. So that's why our choice. And so that this is xt by formal definition. There is a question.
Guilherme is asking why it's called collision time.
I hope I answered to your question. So, okay, times because the process xt move at constant velocity. So the length of this path will correspond to the time up to a certain moment, up to it will reach the n point of the environment, will correspond to the time it will need to reach them, because the velocity is 1. Collision because we are thinking that at every time the process reach a point of the environment, we have a kind of collision. I mean, this is the collision that physically provide the random motion. There is also Milton that in the chat that want to ask for a question.
Go ahead, Milton.
Hi, Alessandra. Yes, that's, so I heard once a guy from physics talking about this maybe it's the same model as, so I just wanted to clarify this. So he said that he put some mirrors in places on the line, and these mirrors they have a 45 degrees angle, which means that sometimes the light is reflected back, and sometimes the light just goes through.
Yes.
So it will be the same model, no?
Yes, it will be the same model, but I mean, in the sense that you are explaining, it was considering a two-dimensional model, I guess.
No, it was one-dimensional, but so there was some device to guarantee that the light gets one-dimensional, no?
Yeah, okay, I understand. Anyway, the answer, I think, so I am quite certain that it is the same, because all this project indeed start from these results on these, they call it Levy blast that appear on Nature. And that were concrete material that were prepared with an amorphous material, and that were able to provide an anomalous diffusion of the light through this length. Okay.
Okay.
With the idea that this was really a two-dimensional material now, but with the idea that there are bubbles that are bubble where the light particle move in a diffusive way. Okay, but then when the motion is outside the sorry, I don't know. When the particle is outside the bubble, it moves in a diffusive way. But when it is in the bubble, it goes straight on. And now, if the bubble has a length that is alpha stable, follow an alpha stable law, this is in relation to the proliferation of this material, you have globally this anomalous diffusion. So this
okay, thank you, Alesandra.
Material, I think, is you're welcome. Sooner or later we will arrive to the two-dimensional model. Okay, I have to probably go a little faster. And so now xt is just essentially, if t is in between two collision, then the process xt has exactly the value of yn plus the interpolation term. And now with this picture, maybe it is more clear. So on the left, you have the discrete time process y that jump from 0 to omega 2, and then to omega minus 1, and then to omega minus 2. And on the right, you have the continuous time process t that realize the same jump, but going straight on at the velocity 1. This means that it will, for example, it will move from 0 to omega 2 in a time t1 that is exactly the length of 0 omega 2, distance between omega 2 and 0, and then so on. And then it will move from omega 2 to omega minus 1 with this pendants of minus 1 line. No, pendants maybe is not correct. Oh, okay, wherever. So at the very end, at this collision time, the process X corresponds to the process, discrete time process Y with corresponding label. Okay, otherwise you have this interpolating term. So essentially we slow down the process Y. Okay. So now essentially the length and the jump of the two processes have no trivial correlation, because each time we jump back to one point, we move of the same length. And so in particular, this means that the transition probability of the two processes are random themselves. So as is customary in this context, we might consider the quench law of the process xt or yn that will be denoted by p omega. This is the law of the process for a fixed environment. Why we refer to an annealed law of the process xt or yn, denoted by p, this ball matti. That is the law obtained by averaging over all possible environments. Okay, now why we are, so our goal, sorry, is to find the scaling limit of these two processes. So we want to derive a function at limit theorem that characterize the scaling and understand if the processes are diffusive or super diffusive and with which exponent. And now, why is interested the process somehow they attracted some researcher? First of all, because indeed, as Barkay, and Klafter find, and in particular Borioni, Caniparoli, and Vezzani with their analysis, that is an analysis, a numerical analysis together with some heuristic arguments, so not totally rigorous, but quite consistent. They find that the annealed second model of the process X is diffusive if alpha is in between 3.5 and 2, and otherwise for smaller alpha is super diffusive with this characteristic exponent. So we want to try to formalize, to make this argument rigorous. And so in the first work with the collaboration with Cristadoro, Lenci, and Ligabon of 2016, what we prove, we analyze just the case of alpha in between 1 and 2. So finite mean, infinite variance of the environment. And then what we prove is that in fact, the process xt and also the process yn, in fact, satisfy a quench central limit theorem. From this is almost immediate to derive an annealed CLT. So for that concern, the situation of alpha in between 1 and 2, there was no diffusive behavior of the two processes. So convergence and law of the process do not implicitly implies that the convergence of the second moment or the behavior of the second moment that was studied in this previous work. Okay, so it was not really in contradiction with the previous results. And also we studied the quench moment also with these two processes, but we couldn't arrive to the annealed moment. More recently, there is a Vamparo now that in 2020 that study again this regime alpha between 1 and 2, in particular by large deviation techniques. He was able to prove that indeed the second moment of the process X is as a diffusive behavior, so increase with T if alpha is in between 3.5 and 2, while if alpha is between 1 and 3.5, one has this super diffusive behavior that completely corresponds with the previous numerical results. Okay, so it's this is to say that somehow is a model which has a richness. Okay, very well. Now let's move to the case of alpha in between 0 and 1, because most of the results I want to focus on regard this situation. Of course, this is the situation that wasn't studied in this previous work, at least not in a rigorous way. Now the point is the following: the environment, indeed, by definition, essentially corresponds to the random walk with the Alphastable law that we mentioned at the very beginning. And so we know that under the scaling n 1 over alpha, we have this weakly convergence to an Alphastable process Z. Y moment explode. Sorry, so Milton is asking for these last results. So this one.
Yeah.
Yes, the Amparo.
Yeah. No, it's not exploding. It's increasing with T.
Yeah, but it's
when alpha is okay. Yeah. It is. Because they have this, by this large deviation, essentially, they can characterize the fluctuation of the process xt. And if I have to tell you intrinsically why, no, I don't remember. But at some point, it was clear to me. Now I really don't remember. It's not my paper, I have to say. But it was quite clear. If you want an heuristic, why? It's okay, Milton.
Yes.
I should think about it. I should look at the paper again, because now I don't remember. Okay, and it is a very recent result. So we have this Alphastable process. Just let me mention that this is a stable process defined on all R. So it's not really a standard stable process that is defined on the positive time, but is obtained essentially by the union of two stable process by reversing the time. Then we have, so the scale process is omega tilde. Then we consider the scale underlying random walk S tilde. This is the usual diffusive scaling that provide a convergence, a weak convergence to a Brownian motion by the invariant principle. And now it turns out that if we scale the process y with this exponent with n to the 1/2 alpha, it is possible. So remember, the process y is essentially the composition of omega and s. If we consider this scaling, we can look at it as a composition of the scale process, the process omega tilde under this subsequence of time square root of n, but whatever, this is the same. And essentially, this makes it quite intuitive the results that we get, the first results that we get concerning this discrete time process. That essentially is the convergence of the final dimensional distribution of the process y tilde under this super-diffusive scaling to the final dimensional distribution of the process z composed with b. Okay, so it's a kind of change of time, but the point is that the time is not the time, is the space, and indeed it is provided by a Brownian motion that might be positive or negative. Okay, now let's move to the process x, that is the most, in a sense, the most delicate. Now, similarly, we have that if we scale this process with n to the 1/alpha plus 1, this can be roughly represented as the composition of three processes. The process omega tilde along an appropriate subsequence of time, the process S tilde, and the inverse of the process of the collision time process suitable rescale. So believe me, is that the point is, if we want to conclude our analysis and derive our functional limit theorem, we need to know the behavior of this collision time process here. Okay, and now the point is that so by definition this is the sum of the length of the walk along each step, but in fact it can be equivalently represented as a summation over all zeta k. Recall that zeta k are all independent in principle, but weighted by this, I will call it local time on the edge, this function that is this graphic n, that did indeed represent the number of times that the underlying random walk S jump over the corresponding edge between k and k plus 1, independently of the direction. So this is a local, what I will call a local time on the edge, which is very related in a sense with the local time on the site. That is indeed very, very common. And now this representation here, that is quite convenient. Why is quite convenient? Because now we have a sum of independent quantity weighted with a random function, but that only depends on the underlying random walk. Okay, this can be thought as a random walking random scenery. So for people who doesn't know who is a random walking random scenery, now it's very easy to define it, or in general, it's quite easy to define it. Let me say that it is an object that was described introduced by a study by Kesten-Spitzer in '79. We are in the same setting of before. So we have an underlying random walk Sn on Z. And then now we have to think that we have a scenery that is provided by this i.i.d. sequence of random variable zeta that are now placed as a weight on the point of Z, that here represent as segments of a different length. But these are weights, and the point is that the random walk random scenery is just the total weight that the random walk collects along its path. So the formal definition is this one. So it's the sum from j from 0 to n of zeta with label sj, and okay, here in the picture I just did a simple example. Okay, and now again, as before, the idea to solve to analyze the behavior of this random walk random scenery, Kesten-Spitzer, they found out that this equivalent representation in terms of the local times of the random walk. Now are really local times on the vertex. So the number of j between 0 and n such that Sj is equal to k. And for the random walking random scenery, they prove in 79 the following convergence of the process under this scaling. I'm essentially focusing on our context, and they reach this. They prove this weakly convergence to the process delta, that is the Kesten-Spitzer process. Okay, and you see here, this is the integral of the local time of the Brownian motion with respect to this semi-martingale, that is where Z is the alpha-stable process. These results, how to say, come exactly from this formula, because you see this summation over Z now become an integral. The local time of the underlying random walk converge to the local time of the Brownian motion, and the zeta k, which are the increment of the environment, converge to the increment of the alpha stable process. So these are quite understandable results. And the point is that this is true for the random walking random scenery. Now, what happens to our collision time? That is a kind of random walking random scenery, but with the scenery where the scenery is on the edge, in a sense. Well, if we add a further hypothesis on the underlying random walk, in the sense that we assume that our steps as a finite moment of order 2 over alpha plus epsilon, something more than 2 over alpha, then we can derive a totally identical convergence of the collision time. And now, not only, but we can prove a joint convergence of these 3 objects that were involved in the definition of the process X. So, of course, omega and S are independent, so this is trivial. The point is that Tn depends on both the 2. And at last, this allows to prove that the finite dimensional distribution of the process X converge to those of the process Z composed B composed delta minus 1 in the notation that I use up to now. So alpha stable process, Brownian motion, Kesten-Spitzer process. As a remark, let me say that if alpha is in between 0 and 1, both processes then display a super-diffusive behavior with this scaling exponent, 1 over 2 alpha for y and 1 over alpha plus 1 for x. Moreover, another remark is that, okay, the theorem states a convergence of a finite dimensional distribution, but in fact, they cannot extend it to a functional limit theorem with respect to a Skorokhov topology, because these limit processes are not Cadillac. So they have discontinuity without outside limits, one-sided limits.
What do you know about this delta process, this Kesten-Spitzer process?
Is almost surely continuous and increasing. This is 0 in 0. That's why I'm taking this inverse. Okay. One can say more. One can say more. It has. It really depends on the choice of alpha and actually of beta. Will come later. That it has cell similar properties, and sometimes is related to it, under some assumption on the parameter. It can. It is a stable process. Okay. Okay, now, because I'm a little in late, now we have the generalized model. Actually, the generalized model that I want to present, so there are some results and then there are some open questions. I'll try to tell you a few important things about that.
We are not very strict on time, so Alessandra.
Okay. No, but I want to use your patience. First of all, the first model is a model in one dimension. It's again a random walk on a point process. The starting idea of this generalization is due to the fact that, in fact, the random walk and random scenery studied by Kesten-Spitzer holds in a more general setting. That is, they have a scenery zeta k represented on Z represented by this family of random variables zeta k that are alpha stable. And in our setting, this corresponds to the environment. So the point process, the interdistance of the point process. And the second ingredient is the underlying random walk that, for Kesten-Spitzer, is in general provided by a sequence of i.i.d. beta stable random variable. So our assumption of having an underlying random walk with finite variance just corresponds to the choice of beta equal to, but it's a particular choice. Now, the question in this context, in this context, Kesten-Spitzer indeed derived the same results as before, essentially. Now, the point is that the scaling exponent depends on both alpha and beta, and the limit has a similar shape of before, but LT is now the local time of a beta stable process. And that's why Claudio was saying that depend on the choice of alpha and beta, one can derive even more properties. Okay, it's not totally general. Okay, so now the question is, can we relax our moment assumption on the underlying random walk? At the very end, we could derive our main theorem, but requiring that the underlying random walk has a finite, not only second moment, but even more 2 over alpha moment. So in this situation, we cannot go to this setting, but the point is that what can we do in this more general situation? And now we can do something if we consider the discrete time process y. Now, the yn is again a composition of omega and s. The representation is the same. The only thing that we have to generalize is the assumption of the underlying random walk. And now the point is that so we could derive a many functional limit theorem depending on the value of alpha and beta. So this allows somehow to tune the behavior that we want to get. If alpha is in between 0 and 1, that means that the environment is infinite mean. Essentially, these guide the motion, lead the motion. And what happens is that if there is a question on the chat?
No question. That I see.
Ah, sorry. If alpha in 0, 1, if also beta, the stability of the underlying random walk is in between 1 and 2, and then this means that we have a finite mean mu that we assume to be different from 0, then essentially the process is driven by the environment, in the sense that scale with an exponent 1 over alpha, and we have this weakly convergence to an alpha stable process, essentially. Notice that this convergence is indeed space of Cadillac function with J2 topology. Let me stress that the topology is the J2 is the best topology that we could have found, in the sense that in topology J1 the result is not true, and not even in topology M1. Okay. Okay. Moreover, instead, if beta is in between 0 and 1, so it is also an infinite mean, or beta is in between 1 and 2, and we assume that the mean is 0, then the process is driven by both, essentially both the motion, meaning that its scale is an exponent that depends on alpha and on beta. Okay, and converge to this composition. Again, this is a convergence of the finite dimensional distribution because this composition of process is not Cadillac. Okay, because as soon one process has a discontinuity and the other process fluctuate around this discontinuity, there are discontinuity on both sides. Okay, sorry, maybe I skip this if no one will ask me. Similarly, if now we consider an environment with finite mean, so alpha is in between 1 and 2, again, depending on the value of beta, we have two possible results. Is also beta is in between 1 and 2 with the finite mean. Of course, the environment has positive mean. When the mean is well defined, it should be positive. Then we have kind of law of large number for the system. So the system increase with n. Okay, we have a trivial convergence, but if beta is in between 0 and 1 or in between 0 and 2, but with the 0 mean, then we have a convergence now in the scorecode J1 topology of the process that is driven by the underlying random walk. So we have a scaling that depends on beta and a convergence to a beta process. And now in this situation here, we can either also straighten the results and look at the fluctuation of the process around the mean. Okay, and we kind of derive a particular situation because I show you all the results. So now the scaling, the global object essentially depends on the specific value of alpha and beta. If beta is smaller than alpha, then is the one that drive the system. So the scaling is with respect to n to the 1 over beta. And the convergence is to a beta stable process. If alpha is smaller than beta, we have the opposite situation. So the motion is driven by the alpha stability of the environment. And if alpha is equal to beta, we have a kind of a composition of the two systems. Let me just stress, it's not trivial to put together all this information because the convergence of sum of processes is not totally trivial in the space of the Cadillac function. So the message is that with this generalization, we can derive many different distinct functional limit theorem, depending on our choice. And at last, this is an open situation. So the study of the process X, if you remember, requires a control on the collision times Tn. And the question is, are these two, the collision time Tn and the underlying random walk, the random walk and random scenery calligraphic Tn, close enough in order to apply the result of Kesten-Spitzer, or in other sense, or equivalently, the two variables denoting respectively the local time or the underlying random walk on the edge and on the vertex are close enough. So what we, in our previous work, in the results that I showed you before, the problem was reduced to the verification to verify this condition, where essentially we have this alpha norm of the difference between you see the local time on the edges and the local time on the vertices weighted with the average length of a step, because this is essentially the point. If our step has a an average length mu, then in average the number of visited edge essentially corresponds to the number of visited site times this length. So, but whatever, this condition was satisfied only under this hypothesis on the moment of the increment of the random walk. Now, the point is that this identity cannot hold in general, because these two quantities, local time on the edge and local time on the vertices, are different or may differ substantially, in particular if beta, so the stability of the underlying random walk is huge. Essentially, the difference is that if we sum up the local time on the vertices over k, we get n. We get a deterministic quantity that is n. But if we sum up over n the local time on the edges, we have a random quantity that depends on the specific step realized by the underlying random walk. And if the steps are infinite mean, the things is also quite difficult. In fact, however, I think this led us to an interesting problem. Sorry, I cannot go on. Let me, sorry. I have to do it again.
Don't worry.
Because it's not working anymore. Okay, let me try with this one. I hope it will appear. Okay. Sorry. I think you see the
perfect.
slide. We are back to our slide. Let me center it. Okay. As I say, this led us to this situation, essentially, to this generalization. On the top, I draw a random walk and random scenery, standard one. Okay, where the scenery is this sequence of random variable placed on the vertices. Okay, and then you have the definition and the example. This is the same as before. And on the bottom, we have a random walk on the scenery, random walk on the scenery where the scenery is on the edge. So the scenery again is the sequence of random variable zeta that are now placed on the edge of the system. Okay. The fact is that, to my knowledge, I didn't know in the mathematical literature an analysis of this kind of problem that seems to me quite reasonable. There is a underlying random walk moving on Z, and then there are weights placed on the edges, and while it moves, it collects these edges. Or at least is not present in the literature under the assumption that the scenery is Alphastable. This is the context studied by Kesten-Spitzer. And in particular, there is almost nothing. I found something in one paper, but just in the case of a simple symmetric random walk, concerning the local time on the edges. So I think this is an interesting model. The second generalization, now I can go quite fast because essentially this is really a work in progress in Cristadoro, Lenci, and Magnanini.
Let me see if I understood. So you say that no results about this second model.
No results.
Okay.
no results, nothing.
Okay.
But I think it's quite, on the other hand, it's quite reasonable as a model, and difficult in a sense. That means that mathematically is interesting. Okay. Now the second generalization go to the two-dimensional model. I will go fast. Essentially, the main issue is to construct a two-dimensional Lévy environment. This means essentially that we want an environment that is not empty, that is low, is stationary and ergodic with respect to the translation, so that we have something simple. And together these two things produce the fact that every point has essentially infinitely many neighbors in each direction. Okay. Subsequent points in each direction. And the third one, if we want to consider a Lévy environment, we want the distance between the coordinate nearest neighbors are also the Alphastable random variable. So if we are in a point and we look above, on the right, on the left, and below, we always find point, and their distance is provided by an Alphastable random variable. And essentially the analysis is after the construction, we want to perform an analysis of the random walk on this point process, and in particular study the problem of recurrences and transients and limit theorems. This is a totally open problem. The fact is that we succeed in construct this kind of environment with a strategy essentially based on an intersect. We first construct a horizontal, say, environment, omega k, by constructing a renewal point process, i.i.d. a renewal point process on each horizontal line of Z2 with alpha-stable intersection, and the same in the second environment, omega v, vertical, again placing this ideal renewal point process on each vertical line. They are not, they do not satisfy our hypothesis because, for example, if we take the horizontal environment, then the distance between points along vertical line may not follow an alpha-stable law. However, if we do properly this construction and we intersect these two environments, we can prove that the resulting process is not empty, actually has the required properties. Okay. So here, for example, you have a point V. These are the points that are neighbors, coordinate neighbors of V, and so on. Now, okay, so the object of interest is this random walk on the Lévy environment, essentially moving between a point X and a point Y with probability 1/3 over 4, if Y is a coordinate neighbors of X. Okay. Now, the simple thing that you might imagine that if we look at this picture, we start from here, then maybe we move on the first neighbors above, then on the right, then below, and so on and so forth. Each step is with probability 1/4. The problem is that there is no underlying structure. So this means that the process Yn cannot be thought now as a composition of these two processes, omega and S. Okay, and you have an example of this. For example, if you take an underlying random walk that move up one step and then right and then down and then left, after this first step it is in 0. But if we take a process Y that follow this rule, is not anymore in 0. Okay, this complicate quite a lot the system. Indeed, it is quite delicate, because let me mention this quite general result that were stated in presenting this paper by Berger and Rosenthal, a very nice paper that is about simple random walk on point process in ZD. Here, the point process they consider is quite general, but essentially with a general, still stationary ergodic and not empty with positive probability. And then they were able to prove that P almost surely in dimension 1, the random walk is recurrent. In dimension 2, the random walk is recurrent is this hypothesis H1 is satisfied. That essentially here this DE denote the distance, the typical distance between 2 points, essentially. Typical, I mean, the distribution is always is the same for every 2 points. So this is the distance between 2 points that are neighbors. And it's transient if the dimension is bigger than 3. So this result essentially keep out only the space where the hypothesis H1 is not satisfied. But the point is that the condition H1 holds if the interdistance have finite second moment, but fails when this interdistance have alpha-stable law with alpha small than 1. In particular, does not hold in our situation. And in fact, Berger and Rosenthal provide a conjecture, provide 2 conjectures. First, they conjecture the existence of a transient 2-dimensional random walk on point process. On the other hand, they conjecture the non-necessity of condition H1 for recurrence. Now, the point is that we don't know if our random walk on the point process is transient or recurrent. So our belief is that it is transient, and we are trying to prove this result. In any case, let me say that whatever we find, we will solve one of these 2 conjectures. Now I really move to the end. Maybe I can conclude briefly. Okay, so we consider Levy-Lorentz gas that we look as a random walk on a random media that in fact is a point process, a renewal point process. The collision time of this process are seen as a kind of random walk or random scenery. Then we have convergence to the Kesten-Spitzer process. And altogether, these show that when alpha is in between 1 and 2, the model displays a quench diffusive behavior, and then also a nil diffusive behavior in the sense that it converges to satisfy a CLT. While if alpha is in between 0 and 1, we have an annealed super-diffusive behavior. Then we pass to this generalized random walk on a point process, where the generalization is considering this beta stable underlying random walk. And again, we obtain functional limit theorem for different range of parameter. Now, concerning the 2-dimensional model, is essentially where we provide an explicit construction of a Lévy-type environment 2-dimension, but we are all the rest is a work in process. Open problems, not even. Thank you very much for the attention. Sorry for being so long.
It's perfect. Thank you very much, Alessandra. So, well, we have no clapping, right? And I turn directly to the questions. So,
yes.
Well, so yeah. Before people ask, so let me go back to this model in which we have randomness on the edges. So where is the problem there? What is the difficulty in this model?
The random walk on, yeah, I tell you again. Sorry, no, in the sense I was very fast. The problem is the following. Usually the nice representation of this process is the one. Let me. Okay, I will draw it. I will write it. the good representation is that T of n is equal. Sorry, I'm seeing a chart moving, so I'm a little bit unstable. The point is that Tn can be written as a sum over all k in zeta of zeta k and then the local time in k. Okay? This is convenient because essentially, as I said before, more or less, this led us to this integral of the local time t of the process, and then the Alphastable. Okay, we have something like that.
Okay, yeah.
Okay. The problem is that while the local time on the vertices is a random variable, right? But if we sum over k, this quantity is equal to n.
Mm-hmm.
Okay. Now, if we do the same thing for this local time on the edge, this is not anymore true.
Yeah.
In principle, you might think that if you take the average, this is more or less equal to what I draw above. So this means the average of the length of the underlying random walk time the sum over k and k in average, but however this is equal to n. Okay.
Yes.
But now the point is that if we consider underlying random walk that is beta stable, this quantity might be infinite.
Mm-hmm.
So it might be extremely large. And even if it's not infinite, is only finite, but still to control the convergence, at least we don't not only need we need a strong control with power alpha, at least this is what we have found. The point is the following. In other words, if we want to use the technology, how to say, the techniques of Kesten-Spitzer, we have to show that these two objects are close, close in a suitable sense. Okay. Otherwise, if we are not able to that, we have really to analyze this quantity, but then we have to study this local time on are not studied before.
Okay. Okay.
More or less.
Well, thanks. So any other questions?
Yes, I have some questions. I mean, if you're patient, I have various questions.
Yeah, I'm very patient.
Okay.
It's nice, meanwhile.
Okay, so the first question is, this Poisson point process, I mean, one should expect that you converge to what sometimes I call the Manhattan Levy process. No, this Levy process that jumps horizontally and vertically, but doesn't jump, that doesn't take any oblique jump, right?
I tell you just one thing. We don't have a Poisson process, Poisson point process. That's the point. I mean, the tail.
Yeah, sorry. Yes.
Okay. No, sorry. Okay. The Manhattan, yeah.
Yeah,
yes.
I mean, you will expect that you will converge to this Manhattan Levy, no?
I'm trying to think what is the exact definition of the Manhattan.
So you put a levy, two independent levies, one on the horizontal line and one in the vertical line, and you construct a levy process in 2 dimensions like that, and this means that you have a process of which you only give horizontal or vertical jumps. You don't allow diagonal jumps. And so I was thinking, because see, this Levy process is actually transient. So
yeah.
maybe, it points, I would say that it points into the direction that your process is transient too, no?
Yeah, but it's different. Okay, now I understand the point. In this Manhattan, so you have this Levy distribution, but you draw it at each step, no? That's it.
Yes, of course.
This is a kind of close to what is called Levy flight.
Yeah, yeah. So I was thinking
discretization. Okay.
Yeah, because that's
and for this, I'm quite sure it is transient.
Yeah.
I'm quite sure it is transient. The point is that here, your steps depend on there is a fixed environment. Okay.
Yeah, but
that you cannot construct in the way you are saying.
I know, but I was thinking that maybe you since you're transient, it means that you only visit a finite number of times each one of them, and then it starts to look like as if you were drawing it independently. No, it's like you know, in these trap models you have something similar. No, that the traps at the end you visit it only a finite number of times, and then
let me say that at some point we have tried to use this idea.
Okay, that's what
of control together with the Levy flights.
It didn't work.
We're not able, but probably we are. No,
it's okay. It's okay.
Probably because we are bad, but so in a sense, this is why we believe that it should be transient. But if we try to solve in this way, we can close the argument. We can't close the argument.
So I'll ask if other people have questions, and then you.
Okay.
But no, you didn't finish, Alessandra. To answer. No. You finished to answer?
Yeah.
To
yes.
Any other question from the audience? Well, if there are no questions, we can return to your question.
Yeah. But okay, so I wanted to do two other comments. But so
I can explain you why. The sense. Okay, it's true that maybe you're essentially independent because you are transient, but now you have to prove that. What is the probability of not having random walk with interlacement? How to say? At some point, no.
Yeah.
You want to measure this, and this is very difficult because now, in particular, you also have it's very difficult in general, but in particular because you have the environment.
Yeah. So there is another thing that two observations now, no more than questions that might be useful for you. So it's in a paper with Thomas Komorowski. So with Thomas, we wrote two papers. One was with Stefano Ola too, and another was not with Stefano Ola. So so the paper with Stefano Ola is more known, and the other one went a little bit unnoticed. And there, in this paper, we use something that we call the plateau convergence.
Okay, so you introduce a new topology.
Yeah, a new topology because we have this.
Space.
So we have this. So the idea is that you have an increasing process like the Kesten. How's called the Kesten-Spitzer process.
Yeah.
And you prove that converges in J1, and then you realize that J1 is not enough. And then you want something stronger than J1.
Really?
Yeah. So we invented this plateau convergence. And the idea is that if you have plateau convergence and then J1 of the other guy, when you compose, you get it's continuous under composition.
Which is always, that's of course quite nice. But not stronger than J1, weaker.
Yes, because for this continuous process with plateaus, I mean, this, we call it plateau because it looks like a cantor.
Yeah. Ah, yes,
So,
I remember. Yeah.
Yeah. So if you have J1, it's not true that you have a plateau converging to a plateau.
Yeah.
And that's the plateau convergence. So you can add that plateaus converge to plateau.
I mean, I was thinking to this plateau. If you have a plateau, you don't converge in J1?
You converge in J1. But what I claim is that okay, so what we did in this paper is that we prove a stronger notion of convergence of a process which is very similar to the Kesten-Spitzer, which is plateau convergence.
Okay.
And when you have plateau convergence, you can compose with another guy that is in J1 and you get something that converges.
My problem is that the composition that I get is not CAD-LAG.
I know. I was also not CAD-LAG.
So you put a topology plateau that even stronger of the J1 to this other space. Oh, I see. I understand. That's interesting.
Yeah, I mean, it might be useful for you. I mean, it's because so you strengthen a little bit your result in the places where you could strengthen a little bit, and then you get something that you can compose. And we have a very similar thing. I mean, we proved various similar theorems. And one of them was exactly what you put on your slide. So we have a composition of two Levy processes on which the problem that was if you jump at the same time, then you don't have convergence, and that's it, no? So
we were already very happy to have derived this convergence with respect to J2 topology. That is horrible, by the way. I don't know why. I mean, I don't know why we at some point insisted proving that, because the M2 was much simpler.
Yeah. But I mean, it's so the idea that in the Kesten-Spitzer, if you strengthen a little bit the topology, then you can take compositions and then you can obtain convergence in a functional convergence of the other guy, no?
Newton, Marcelo raised his hand. Marcelo, you want to ask some question?
Yeah. Hi, Alessandra.
Hello, I'm Marcelo.
Hey, it's maybe a very naive question, but have you thought of any situation that it's also interesting to put some dynamics in the environment? Like you still have these point processes or these renewals, and the environment evolves in time as well. Is it possible to make something interesting in this line?
For sure is interesting, but we didn't thought about, because imagine we are far away, we are in a one-dimensional system. Already the generalization to two-dimension, but it's true that as a one-dimensional model, one can start to think even to this generalized moving environment. Why not?
Okay.
What in general I can tell you, if physical model physicists do is to, for example, it's not really the same thing, but is consider this process X, this continuum time process that do the interpolation. They take random velocity at each path. So the trajectory is the same, but now you have a random velocity that somehow is maybe a dual point of view of moving the target, the point. Not really, but I know that they are interested in that and they look at that, but we didn't at all look at this. At this moment, we are quite concentrated on this two-dimensional system, and it's something that I'm going to conclude, but it goes in another direction. Essentially, we have a kind of Spitzer identity, which is a Sparre-Andersen identity. Essentially, is an identity for the generating function that allows you to characterize, for example, the first passage time or first ladder quantities, and the XML essentially. So this essentially conclude my mental space.
So, Alesandra, I wanted to comment one last thing, if it's possible.
For sure.
Because it's so I have to do a little bit of publicity because it's the PhD thesis of my student Leandro Chiarini, part of his PhD thesis, no?
You have to.
Yeah, and so what he proved is that so it's something very elementary, but it was not really in the literature. That's so when you have a Alphastable law and you want to prove the CLT, he gets the first order correction to the CLT. Okay, so you have something a little bit more quantitative, no? So you can so basically what he can prove is that when you look at the Levy process,
this is very interesting.
Depending on the conditions, what you can do is that you can improve the rate of convergence of your Levy processes by adding a little bit of random walk. So it's like you have a Levy a sum of Alphastable laws, and then you sum and you converge to this Levy process, right?
Yeah.
But the first order correction is a very small Brownian motion.
Really?
Yeah.
Always?
Not always. There are conditions. But in principle, in his paper, the methodology allows you to, for example, to prove that the first order condition is another Levy process of higher alpha.
This is interesting, really, in connection to the problem that I'm studying, because if one has the first order of fluctuation, clearly, so it's nice that you told me about this paper. So not only you advertise, but I can also maybe cite.
yeah, because it's
it's on the archive, I guess. Maybe it's published, I don't know.
No, it's on the archive, I think. Let me just check because if
whatever. Leandro Chiarini.
Yeah.
It's an Italian name.
Yeah, exactly. Okay, yes, it's on the archive. So it's on the archive, so it's so you can check take a look if you want. It's very recent paper. So it was submitted in 5 of January, so 1 month ago.
Very nice.
And so the methodology allows you to do that, basically, that you have this Alphastable and you converge to the Levy process, and the first order correction, depending on how is the decay of your Alphastable law, is going to be something else, no? That you can characterize, even a Levy process or maybe a Brownian motion. And that could be useful when you take this, when you're taking these limits, no?
Yes, definitely.
Okay, so
I mean, the first order fluctuation helps in any analysis. I mean, is helpful if I understand the kind of setting. Thanks a lot, Milton.
No, you're welcome.
I took notes.
Yeah. And thanks to you for the very nice talk.
Thank you. I hope I was very slow at the beginning and at the end.
Very clear. Thank you a lot, Alesandra.
Thanks to you.
See you in Brazil.
So I wish you all the best and I hope to see you physically at some point.
Good. Bye-bye.
Bye. Thank you.